Hey everybody. Today we're talking about confidence intervals for the mean in the situation where the population standard deviation sigma is not known to us. The confidence interval that we're ultimately going to come up with looks a lot like the confidence interval when sigma is known, but with some really important differences. And to see those most clearly, I want to back up and start with the confidence interval for the mean when sigma is known. It has this form, x bar plus or minus z star sigma divided by the square root of n. And there's a couple of really important pieces here to understand before we go any further with this. Sigma divided by square root of n is the standard deviation of x bar, of the sample mean. So you imagine many different samples, many different x bars. Sigma over square root of n gives a measure of how spread out those will be from one another. Z star is the critical z-score corresponding to the confidence level C. So what we do is we draw a standard normal distribution, n of 0, 1, and we want to capture C% of the area under that graph between negative z star and positive z star. Now, because there's only a few confidence levels in common usage, we can usually just do this directly from a table. We look up the confidence level C, we get the z star back. For instance, when C is 95%, z star is going to be 1.960. When the population standard deviation sigma is unknown, we do the obvious thing, estimate it with the sample standard deviation S in this formula. That introduces some additional uncertainty because now in each new sample, not only does x bar change, but S changes as well, whereas sigma does not. We account for this additional uncertainty by using a t-distribution instead of the standard normal. So here I've drawn a picture that's relevant. T star is the critical t value corresponding to the confidence level in the distribution t of n-1, just as z star was the critical z value corresponding to that confidence level under the standard normal curve. The expression s divided by the square root of n in that formula is called the standard error of the sample mean x bar. It quantifies the variability of the statistic from sample to sample. Another way of viewing that is that it is estimating the standard deviation of the sample mean x bar, which we know is sigma divided by the square root of n. The value t star describes how many standard errors are needed to achieve the desired level of confidence. So let's get into calculating t star. It's the value such that the probability that t is randomly between negative t star and positive t star is c. Since we have a probability and need to find a value, it's going to be an inverse calculation in this t-distribution. Unfortunately, when we do calculations like this, we're going to need the area to the left of the value t star, not in between them. So we're going to have to use a little geometry and do a little bit of arithmetic. If the area between negative t star and positive t star is c, the area left out is 1 minus c. And so each tail has to have half of that area. In this picture, I'm showing an example where C is 95%. That's the most common confidence level in use. That means that if the area in between is 95%, there has to be 5% left out on the ends. So that means 2.5% left out on the left, 2.5% left out on the right. Therefore, 97.5% of the area lies to the left of T star, and that's what I have shaded here. That's the value we need to pass to our inverse cumulative distribution function. In R, the inverse CDF is represented by QT, and you need to pass it the area to the left, here I've denoted that P, and the number of degrees of freedom. When you're computing a confidence interval for the mean, the number of degrees of freedom is always one less than the sample size, n. So that's why I've labeled this curve T of n-1. In other words, T star is QT of P, n-1. For instance, if we're at a 95% level of confidence with n equals 25, the necessary command to find the t star value is qt 0.975, 24, 24 being 1 less than 25. The result of that is 2.064. There is a formula for the area to the left of T star for any confidence level C. It's 1/2 times 1 plus C. But for most people, the picture is easier to remember than the formula. And the arithmetic that you need to do just using the picture isn't that hard. All right, let's do a full example. Researchers wish to investigate the sodium concentrations in a Canadian lake. So they collect 23 samples from different places in the lake. We'll view that as a simple random sample. finding a mean of 24.7 parts per million and a standard deviation of 4.2 parts per million. Construct a level 90% confidence interval for the mean sodium concentration in the lake. So I recommend that you pause the video here and give this a try on your own before seeing my solution. So in this case, we're given that x bar is 24.7, the sample mean, s is 4.2, the sample standard deviation, and n is 23. It's important to notice that this is a sample standard deviation, not a population standard deviation. So we need to find the critical value for the confidence interval using a t-distribution, not a normal distribution. So in this case, we're going to be using confidence level 90%, and we're going to be working in t of 22 since the sample size is 23. The picture looks like this. I've drawn 90% in the middle. By symmetry, there's 10% left off, and so 5% is left off on the left. We need to find the value t star in t of 22 with 95% of its area to the left. And so we need to use the command qt of 0.95, 22. And we evaluate that, and the result is 1.717. Plugging everything in, we get a confidence interval of 24.7 plus or minus 1.5. And of course, the units here are parts per million. So to say this a little bit differently, with 90% confidence, the population mean lies between 23.2 and 26.2 parts per million. To say this a bit more specifically and a bit more technically, 90% of the time that we use this process, 90% of the time that we go out and get a sample of this size from this population, the resulting interval will include the true population mean mu.